Hello, welcome back. The title of this lesson is called Position and Velocity in 2 dimensions and 3 dimensions. So this is critically important material because now we move beyond one-dimensional motion, which we've done in the past. That's motion along a straight line, either horizontally or vertically due to gravity. And here we begin to consider what happens when we have 2 dimensions of motion here. For instance, if you throw a baseball, it's going to fly in what we're going to learn later is a parabolic path, the path of a parabola. So it's going to go up, but it's also going to go horizontal at the same time and of course, carve out or trace out a curved path. So we're going to learn about two-dimensional, how to handle position and velocity in 2 dimensions in this lesson. In the next lesson, we're going to handle acceleration. That's its own thing. We're going to talk about that in the next lesson, but you have to understand this in order to understand acceleration. Now, let me tell you a quick story, and I want you to really hear what I'm trying to tell you here. I could just give you a few equations, and you could probably solve the great vast majority of the problems using those equations. I could literally write the equations down in about 2 or 3 minutes, and we could just solve a bunch of problems. That's what I did when I was younger. I learned the equations, and okay, I understood how to work with them. But then I didn't totally understand the true fullness of what I'm about to teach you here in terms of how the vectors actually worked. I didn't understand that until much, much later when I was starting to study much more advanced topics called tensors and tensor analysis with relativity theory, much more advanced things down the road. I didn't fully understand what that was trying to tell me because I never fully understand how these basic ideas of vectors in 2 and 3 dimensions work here at this level. So what I'm going to do is I'm going to front load this to you because I want you to understand it early. This is going to be more of a theory lesson of how the vectors work in 2 dimensions, which are then also extendable or extensible to 3 dimensions for position and velocity. And then in the next lesson, we're going to use everything we've learned here to talk about acceleration. Once we have that, then we can talk about projectile motion, the motion of baseballs and things like that, and it gives you the keys to the kingdom because then you can talk about planetary motion, motion of the planets around a sun, or even atomic motion we can talk about using the tools I'm going to give you here. So please resist the urge to skip past this theory. I know you're going to look at it and you're going to be like, I don't want to see all that stuff. I'll just give me the equations. Give me. But the problem with that is if you short circuit your understanding now, you will severely handicap yourself later. Trust me, I've been there. So we're going to put the train on the tracks here in the beginning. We're going to do it right. So follow me step by step. I promise it will be absolutely clear. Now, the first thing is that we have to recall what we already know. So we're going to recall. Recall in 1 dimension. Motion in 1 dimension. We've already done that in lessons past. We've actually solved lots of problems in 1 dimension. This is supposed to be recall. Sorry about that. Like that. All right. What did we learn in the past? We learned that if we want to figure out if there's only motion along a straight line back and forth in the x direction, like this is what we did before, we learned that the average velocity in the x direction, that's what this means. The average velocity in the x direction was just x2 minus x1 over time 2 minus time 1. All this means, when you subtract the x's, it means you figure out how far the thing moved, position 2 minus position 1, that's how far it moved, and you just divide t2 minus t1 is how much time elapsed. Distance divided by time. That's the average velocity, and we use a shorthand notation, and we say that that's delta x over delta t. So we learned that before. This is just, a kind of a trip down memory lane, so to speak. All right. And then we also learned that this was called average velocity, right? That's what that was called. And then we learned that the instantaneous velocity, which is the average velocity, is what's happening between 2 points. Some particle flies from here. It could be a curved path to some final destination. The average is just taking into account the end points, point 1 and point 2, position 1, position 2 along the x direction here in 1 dimension, divided by the time. But we also have this idea of an instantaneous velocity, which we wrote down before, which was the limit as delta t goes to 0 of delta x over delta t. Now, this stuff looks very complicated, but what this is not complicated. It's the instantaneous velocity. That's what instantaneous means here. Instantaneous velocity, average velocity. Now what this means, and again, we've already done this in past lessons, so if you're completely lost, you have to go back to those previous lessons, is basically The average velocity is looking at 2 points in space and 2 points in time, and you find the change in position along x and the change in time, and you divide them, you get meters per second. But then we said, well, we're going to shrink the distance smaller and smaller. We're going to shrink the time interval, which makes the points come, the starting and ending points come infinitely close together. And when we take a look at what's happening on a very, very, very short time interval, call it infinitely small time interval, how far did it move and how long did it take? We call that the instantaneous velocity. Instead of two endpoints separated far in time and space, we just shrink everything down and we just consider how far does the particle move in an insignificant amount of time. That's why delta t goes to 0. And of course, it's going to move a teeny tiny distance also. And we take this teeny tiny distance divided by this teeny tiny time. As it continues to shrink down to 0, distance divided by time, that's called the instantaneous velocity at a single point. Again, only in one dimension, because this is a review of what we already know. Now we're going to generalize these ideas to when the motion is not in one dimension. What happens when the motion takes a curved path through space? Two-dimensional space, or even three-dimensional space. And I can tell you the punchline right now. You can always consider any motion through space to be, you can consider to be one single motion, like a curved path, but you could also break it up into components, vector components, the x component of the motion along the x direction, and then the y component of the motion along the vertical direction. Breaking apart a vector, I think, is something I taught you way back in one of the first lessons, is one of the central core ideas in physics. It really is used constantly in everything from motion, acceleration. We use it in fluids, when fluids flow. We use it for magnetic fields. We use it in atomic phenomena. Basically, anytime something is moving or changing, you can break it up into the components. In this case, we're going to be talking about motion of a curved path. So we're going to treat the motion in our mind as acting separately along a horizontal direction and then also separately in a vertical direction, and the addition of those two motions is what actually causes the path to look curved to us. So every time you throw a baseball or toss anything, I want you, instead of picturing that perfect path, I want you to consider it to be really two different motions happening. One is a purely horizontal motion, one is a purely up and down vertical motion. Working with those together is what translates this guy into the curved path that we see. That's what we're going to do. So now we know where we have come from. We know what the average velocity is, and we know what the instantaneous velocity is. According to these equations, we've already kind of done these. Now we need to talk about 2 dimensions and 3 dimensions. We need to figure out how to record a position of a point in space. When it's just one dimension, it's just a number line, so the point is like right here, x is equal to 5. But how do we do it when we have 2 dimensions, x and y? Let's draw a picture about that. So let's talk about in 2D space. Keep in mind that all of these ideas also apply to 3 dimensions. We're going to talk about that later as well. So let's draw a little xy graph here. So this is x. Let me make sure I didn't hog the board up, because I'm going to draw one more of these guys. This is x and this is y. I think I can go maybe a little bit farther back here, something like this. This is x and this is y. So instead of 1 dimension of motion, we now have 2 dimensions of motion to consider, right? So what I want to do is I want to give you an idea of what the path of this thing is going to look like. We're going to use the same path for all of them. And so this is like a curved path, something like this. You can imagine someone launching a baseball, which then takes this path, and I'm stopping right here, but as you know, it's going to continue going. It's going to hit the ground like this. When we talk about 2-dimensional motion, this is what we're talking about. There's a horizontal aspect of the motion. That is what's sending it down that direction, down range. But we also have a vertical component of the motion, which is the up and down. That's how high it gets. So when you start to look at motions like this, I want you in your mind to mentally break them up into how is it moving horizontally and how is it moving vertically. Of course, if I only look at the vertical motion, it goes up and then it eventually comes back down and hits the ground as the path were to continue this direction. All right. Now what we have to do is we have to superimpose on top of this some point. So I'm going to put some point right here, and we're going to call it point P. This is just a point in space. Of course, as time goes on, this could be the baseball, the ball continues to fly along the path here, right? Now, how do we bookkeep the position of P? Obviously P, the point, the ball is going to move with time. How do we bookkeep its position? The way we bookkeep its position is we draw a vector arrow straight from the ball, not along the path, but a straight line with a vector arrowhead like this, straight to the origin. And the tip of this arrow bookkeeps and tells us where the position of the ball is. Now that by itself is already a little weird. The first time you see the tip of an arrow to be the placeholder for where the ball is, it's a little bit weird, but you have to get used to that. You have to have some way of keeping track of the coordinates of the ball. So we have XY coordinates of this ball. And what are the XY coordinates? Well, if we go over here to something like this, we draw like a little, something like this. We say this is the X coordinate of the position of this ball. And right here, this is the Y coordinate right here. So at this point in time, the coordinates might be X is equal to 2, Y is equal to 3. And then over here, when the ball is here, the coordinates might be X is equal to 5 and Y is equal to like 7 or something like this. And if you could see the coordinates with your mind, as you start the clock, the ball is going to trace out a path, and at every moment in time, it'll have a different set of XY coordinates. That'll be constantly changing as the ball moves. The X coordinate will change and the Y coordinate will change. And if we bookkeep the X and Y coordinate as a coordinate pair, where the point here forms the tip of an arrow, then as the ball flies, the arrow lengthens and basically traces out a longer arrow as the path goes. So for instance, if the ball ends up here, then the new position vector will go straight to the origin to this place. If the ball is here, the tip of the arrow will go right here. So we have not used vectors that much. We have to start to use the idea of a vector. A vector has magnitude, length, and direction. And you can see that as this ball flies, if we use the tip of an arrow, a vector arrow, to bookkeep the position, XY coordinates of the ball, then as the ball flies, the arrow is going to move. The tip of the arrow moves. And the arrow is going to get longer as the ball gets farther away, indicating it's farther away from the origin. And the angle of this arrow is going to change too. As it traces a path all the way here, the vector line will go very, very, very close to the ground, eventually getting exactly parallel with the ground as the ball contacts the ground. But as the ball flies, this arrow is like a living thing. It moves and it changes. Of course, it gets lengthens and it changes angle and things like this. Now, this vector that we have constructed right here, this vector right here, we call this the vector R. In general, R is what we call the position vector. So point P is just the point of the tip. But the actual vector itself, the arrow itself, we call it R, and we put a line with an arrow on top, and this means vector quantity. So you're going to see these vector quantities all the time. Now, if I just wrote equations down, they're going to have vectors in there, and it's very easy to overlook the arrows and to realize they're vectors. It's very easy to ignore them. But you need to remember that all quantities you see with an arrow on top are called vectors, and they're all arrows, and they have a length and they have an angle. So again, this is the position vector, but later on we're going to have a velocity vector. That's going to tell you the direction the velocity is going. Right now, this is not anything to do with speed. This is just where the particle or the baseball is. But we'll have a velocity vector later. And then we will have an acceleration vector, which is telling you how much and what direction it's accelerating. And then much, much, much later, we will have momentum vectors, and we will have electric field vectors, and we'll have magnetic field vectors. We'll have vectors for all kinds of things, which just bookkeep how large the thing is you're talking about and what direction it points, because vectors have a direction as well. So the length of this arrow determines how big or how far away from the origin the particle is, and of course the angle specifies the direction that the particle is in relation to the origin. So, for instance, I can say note, I can say that when we talk about a vector, if we want to just talk about how long the vector is, we put these bars around it. And this is telling us, here's a vector, I want you to tell me how long it is. That means literally if you got a ruler and measured how long the vector is, then how long is it? That's it. This is called the magnitude of the vector, right? And you can see that if this is a triangle, a right triangle, and this is the x, and this is the y, this is y, right? Goes up to the y position here. So this is a distance of y, this is the distance of x. From the Pythagorean theorem, the square root of x squared plus y squared tells me how far away from the origin this ball is. So if I know the x-coordinate and I know the y-coordinate, and I put it in here and square x and square y, and then take the square root, because x squared plus y squared is equal to the magnitude of r squared, then the magnitude of r, once I take the square root from the Pythagorean theorem, is just equal to this squared plus this squared, and then you take the square root. All right? And now we have to consider what happens as this ball flies a little bit farther. So let's go and draw a picture down in the future. A little bit down in the future. So I'm going to draw another one of these guys. I'm going to do a lot of drawings over and over and over again. So they're not going to be identical, but you're just going to have to work with, because I'm not a human computer or a robot. I cannot draw them exactly the same. So you're going to have to imagine the pink path is the same as the pink path. And what we're trying to denote here now is that originally in drawing number 1, the ball started out, I guess, when we took a snapshot in time, we called it point P. Now I'm going to call it point P1 because I'm going to draw a separate point down here, which is going to be called point number 2. So sometime later, the ball has traveled to a new position. All right, now, how do we keep track of these positions? We just said that this one is bookkept by drawing an arrow called a vector to the origin. And this arrow has a length, a magnitude, and an angle to the origin, and those two numbers uniquely identify the tip of this point. You can also consider the x and y coordinate as being similar information there. So this was called R1. See, I called it vector R right here. Now I'm going to call it vector R1, pointing to P1. Now, what happens when the ball gets a little farther down the line? Well, now I have to bookkeep its position here, and I'm going to mess this up, almost certainly. Let me erase this. This is R1, vector arrow. So I'm almost certainly going to mess this up, so please bear with me. It's going to hit the origin right here. I knew I would collide with that. That's okay. There's R1. Actually, I'm going to erase this right here. This is called R1, this vector right here, and this one is called R2 because it's pointing to position number 2. You see what's happening? As time goes on, as the ball moves, the arrow gets longer and the angle of the arrow changes. So this is a new vector. This is a vector pointing here. This is a vector pointing here. The tip of the vector just bookkeeps and keeps track of where this object is as time goes on. Why am I doing this? Because if you look back at the original situation, we wanted to figure out what the velocity was between 2 points in space. In one dimension, all we did was, it was very simple. In one dimension, it was like, okay, it starts here, and then it ends over here. The distance is just x2 minus x1, that's the distance. But here, the path traveled is much more complex. It didn't travel a straight line path, it traveled a curved path, but we still have to subtract the end point minus the beginning point somehow. But now we're bookkeeping everything in terms of a vector because it's got a point anywhere in space. So what do you think, how do you think we're going to write down the average velocity of this guy? The average velocity in one-dimensional space was the distance traveled there divided by the time, delta x divided by delta t. Well, here, let me switch colors just to break it up a little bit. The average velocity, no longer in the x direction, just in general, the average velocity is going to be position vector number 2 minus position vector number 1, and we divide by t2 minus t1. You see, it's exactly the same thing. It's position number 2 minus position number 1 vector divided by the time elapsed. That's what we call the average velocity. It's the same thing, x2 minus x1 over the time elapsed. Exactly the same thing. It's just that before, it was only in one direction. Here, the particle can move, in this case, we're having two-dimensional space anywhere in the xy plane, but I could expand it to three-dimensional space, x, y, and z. I may start here, xy, z coordinates here, and then the ball may be over here, xy, z coordinates number 2, way away from me over there, and the difference between the two, position vector number 2 minus position vector number 1 over here, that's going to be some measurement of how far the ball moved in that interval of time. So we bookkeep it as position vector number 2 minus position vector number 1 divided by the time elapsed. Exactly the same thing. This is meters per second, but these are vectors now, not just numbers. Notice there's no vector symbol there, but there is down here. So the way we write it in shorthand form is we say this is delta r over delta t. This is the change in the position divided by the change in the time. So you're going to hear me say over and over again through this lesson, rate of change, rate of change, rate of change. What this is saying is the average velocity between 2 points in space is the rate of change of the position with respect to time. If you're taking calculus, and this is not, we're not getting heavy into calculus right now, but if you're taking calculus, you recognize this is getting close to the definition of what we call a derivative in calculus. It's all related to what we're doing right here. I'm not going to go down too far down that road, but you should see some similarities if you're taking calculus. If you're not taking calculus, that's fine, because you don't need it, for this particular lesson anyway. So we have established that we can bookkeep the path of a ball using a vector. We call the first vector in position 1 R1, and which are the xy coordinates of this point, and we call the position vector number 2 the second arrow, which involve the xy coordinates of point number 2. And then we're saying that the average velocity is the final position minus the initial position in vector form divided by the time elapsed. In shorthand way, we call it delta r vector over delta t. Now, how do we actually graphically show and calculate what the average velocity is? What I want to do is actually subtract these vectors here. So let's go over and draw a picture on this board on exactly how to do that. So I'm going to draw another little axis like this. And of course, this is going to be x, and this is going to be y. I told you I would be, drawing the same picture over and over again. I could cheat, I could like not even care and don't even draw this, but I'm trying to make it where you understand what's going on. I'm telling you, this kind of stuff is very, very important to understand. All right, so here in the beginning, we have position P1, right? So let me draw that right here. We're going to call this P1. And then over here, we have P2. Nothing has really changed, P sub 2. All right? So what we want to do to find the average velocity is to take position vector number 2 minus position vector number 1. And we already learned in the past how to add vectors graphically and how to subtract them. If you add vectors graphically, you put the vectors head to tail, and then you draw an arrow from start to finish. But we're not adding these vectors, we're actually subtracting them. So we have to start with position vector 2 and subtract position vector number 1. Now, what was position vector number 2? If I can draw a straight line, which I'm almost certainly not going to be able to do, it goes something like this, straight like that. Okay, that's not exactly straight, that's pretty close. So here's position vector number 2, and what we want to do is subtract position vector number 1. All right, how do we subtract? What we do is we take position vector number 1 and we flip it in the opposite direction, making it negative position vector number 1. That's how we pull off subtraction. In order to subtract a vector, you take the second vector and you flip its direction, which makes it a negative vector, like this. You go down here and draw this. Oh, I already messed up. You draw it down toward the origin like this. So there's your arrowhead going this direction, and this is negative R1 vector. Remember, the original vector pointed from the origin to the particle. If you keep everything the same, but you just flip the direction, it becomes negative R1 vector. And then to pull off the subtraction, R2 plus a negative R1 is the same as R2 minus R1. So how do you add these vectors? See, it's already head to tail. It's already, here's the head, here's the tail, and there's the other head. So in order to actually subtract these, R2 minus R1, you just take this one and you connect it like this. Like this. And what you have here is R2 vector minus R1 vector. So in order to calculate the average velocity, we have to take R2 vector minus R1 vector, and that's what we did, right? That's what we did. So then, what do we have to do in order to finish this guy up? What we want to do, I think, is I want to clean this drawing up. So let's go and redraw it over here. I told you I'd be redrawing these things a lot. Bear with me. Here's X. Here's Y. I know it may seem like a waste of time to draw this over and over again, but what it also does is it gives you time to process what's going on, because anybody watching this thinking, oh yeah, I got it in like 5 seconds, you probably don't have it. You probably just think you do. So a lot of times things take time to bake in the oven. So here again, we had position P1 of the ball, and here we had position P2 of the ball. What we're basically saying is that if this was the position vector of R2, this was the position vector of R1, but we want to subtract it, so we flip it around to make it negative. And then when we add these, which is the same as making R2 minus R1, the resultant actually is a vector that starts from P1 and ends at P2. So now, instead of drawing all that other stuff to clutter the diagram, I'm going to show you that when you do that, this is what you end up with. This one, r2 minus r1. These are both vectors, like this. So that's the vector going from here to here. What have we figured out? When you have a ball that starts at position 1 and ends at some position 2 down the road, then when you subtract the vectors, r2 minus r1, the resultant of what happens when you figure out how far the thing moves. Remember, we're doing the exact same thing that we did in one dimension, x2 minus x1, but it was simple because it was only in one direction. Here, we're using vectors to take the final position minus the initial position, and what you get is an arrow that starts from the starting point and ends at the ending point. That's a displacement vector showing basically where the ball moved between these 2 points. This arrow is telling you how far and in what direction the ball moved from point 1 to point 2. I mean, it's not super rocket science. I mean, if I had just drawn that arrow, you could have convinced yourself, oh yeah, it goes from starting to ending, so the arrow must go that way. But I wanted to tie it into the definition of average velocity and show you that when you take r2 minus r1, and then you flip that one around and you add them, what you get is the resultant that goes from start to finish, like this. All right? So the displacement vector points from P1 to P2, and it's called R1 vector, R2 vector minus R1 vector. Now don't forget that the average velocity, I forgot to put my little vector arrow here. The vector that defines the average velocity is the change in position divided by however much time elapses. So I think I'm going to write that down over here just to remind you that the average velocity as a vector is just equal to how far the ball moves, or the change in position divided by the change in time. All right, so what we found here is just the top part, the change in position. So what is the actual velocity? Well, you have to take this vector and you're dividing it by just a number here. Time is just a number, it's not a new vector. So what you're getting is some velocity. I'm going to draw it parallel, same direction. I'm going to call it average velocity. So to summarize, what you have is the ball that's going through a path. In one snapshot of time, it's in P1. In the final position, it's in P2. And to calculate its average velocity in terms of a vector, what you do is you take its final position in vector form minus its initial position in vector form. When you do that, when you do the vector subtraction correctly, it's an arrow, a vector that goes from the starting point to the ending point, literally just showing you how the ball moved through space. And then you take that vector, which is this, and you divide by a number, which is time. So the velocity is a vector in exactly the same direction, but it's either going to be bigger or smaller than this, because when you take a vector and you divide it or multiply it by a number, it stays in the same position. It stays oriented in the same position, but it's either going to be bigger or smaller. So that's why I drew it, in this case, a little smaller. But whatever it is, it's going to be pointing in this same direction. So we have gotten to the point where now you should understand that the average velocity in vector form, why it produces an arrow that points from the starting to the ending position. So now what we want to do is we want to start to think of in terms of components. So let's talk about components of the velocity. Right? Because, right now we're kind of considering the entire path, but I told you in the beginning, we really want to understand the x direction and the y direction separately. Those are the components. So what we can do is we can think of, right now we have one equation for the entire vector, the whole enchilada, all directions at once, but we can break this into an x equation and a y equation. And we can say that the average velocity in the x direction is equal to how far the thing goes in the x direction divided by how many seconds it takes between the 2 points. And then we could say that the average velocity in the y direction was how far the thing goes in the y direction divided by delta t. What I'm trying to tell you here is that all motion in 2 dimensions is a mixture of an x motion and a y motion. If the particle goes toward the camera as well, like a third dimension, then it would have x, y, and z components. And we can, not only can we, but we have to consider all of those motions separately in order to be able to solve any problems. So here we considered the entire vector with arrows showing you that the vector velocity is delta r vector divided by delta t. So we're kind of considering all of the motion together here as one composite. But you can break this down and say, okay, well, you can consider the average velocity in the x direction to be how far did it go only in the x direction. Notice that This, if the ball travels along this path, it only went this far in the x direction. That would go here. Then you would divide by time. That would be the average velocity only in the x direction, okay? And then separately, you could say, how far did this ball travel up? Well, you can see the ball only got to here, so it only went this far up. This is the vertical distance y, delta y. Again, you divide by the number of seconds and you would get a vertical average velocity. So here you have a horizontal average velocity and a vertical average velocity. So this motion you could consider as a composite average velocity, but you can consider a component of horizontalness to this motion, the horizontal velocity, and the vertical velocity. And the sum of those velocities together is what produces the final result. I keep harping on this over and over because for every problem, it'll be like, a cannonball is fired at 30 degrees at this velocity, you know, how high does it get or how far does it go or something like that, or does it hit whatever in the sky? So the first thing is going to be, okay, what's its horizontal velocity? What's its vertical velocity? And then we consider them completely separate because the sum of those velocities, one acting up and down and one acting only horizontal, they yield the curved path motion. And as the ball flies through the air, the strengths of the vertical, or the magnitudes of the vertical and the horizontal velocities are changing as the ball flies through the air, tracing out that curved path. All right? So we're saying the vector equation that gives you the average velocity is a vector equation, and that gives the whole thing. But you can consider the components, only the x direction divided by time. The y direction divided by time can give you these average velocities in terms of components. So now what we want to do is turn our attention to instantaneous velocity. Instantaneous velocity. Now in the one dimension, we already said the average velocity was delta x over delta t, and then we said, okay, if you want to figure out the instantaneous velocity at one exact tiny little moment of time, what you do is you let the time interval get very, very small, approaching zero, so the particle doesn't move very far, but it does move some, and then you just let that get smaller and smaller and smaller, and you measure how far does it move, and how long does it take to move, and then if you make that interval smaller, then you can define the velocity at this point. And we're going to do the same thing through the air. As the particle flies through the air, it has an instantaneous speed here, and an instantaneous velocity here, and an instantaneous velocity here. And because the path is comprised of an infinite number of points, as the ball, every little nanosecond is in a tiny little different position, it has an infinite number of instantaneous velocities, which is always changing as the ball flies through the air. So we want to figure out how we can kind of bridge the gap and figure out what the instantaneous velocity is there as well. So we're going to draw a bunch of pictures. And I'm not sure I can fit all four of them there. I'm going to try though. So, because it would be great if I could fit all four of them. So let me kind of draw this first one. This is x, and this is y. And then I'm going to go over here, and I'm going to draw this one right here. And this is x, and this is y. And then if it works out here, then I'm going to draw down below. So it's basically the exact same sort of thing. We're going to have a curved path like this, right? Now we're going to redraw what we've kind of already done before. We have point P1. Let's see here, how do I want to do this? P1, and then we have some point over here, we call it P sub 2. Now we just said that to figure out the velocity, we have to subtract there's a position vector that points to P2, and there's a separate position vector that points to P1 here, and when you subtract them, what you get is let me switch colors. You get a vector that points from P1 to P2, and this vector we said was the difference, the difference there, and then we said that the average velocity as a vector was delta r delta t. So how far, or what's the change in position divided by the change in the time? Then the initial position was R2, the initial position was R1, the final position was R2, R2 minus R1, we had to flip it, then we had the resultant, which is pointing from start to finish. That's what I'm drawing here. The vector here from start to finish, this is R2 minus R1, delta R. This is delta R right here. So in other words, this vector right here, this one, is delta R. And that's what's on top. Once we divide by delta t, then we end up with some velocity in that direction, right? Now, how do we get an instantaneous velocity? What we want to do now is this is what we call separated in time. P1 and P2 separated in time. Now, in order to get an instantaneous, what we want to do is bring P2 closer to P1. So let's bring it a little bit closer, not too close. Let's just bring it a little bit closer and see what happens. So we're going to go and draw the exact same thing. Whoops, let me not do a little arrow right there. Like this. And what we'll basically say is we'll keep P1 in exactly the same place, but P2, let's bring it closer. Let's bring it to maybe about halfway. Something like this. So here's P2. So we'll do the same sort of thing. So we have a vector pointed to P2. We have a vector pointed to P1. We want to figure out the velocity. We have to take this vector minus this vector and divide by the time. And when we do that, what we figured out is that we get an arrow or a vector that goes from the start to the finish. And this vector is delta r, right? And the velocity, average, is equal to delta r divided by delta t. And now that arrow is smaller. So it's a smaller arrow, but it's also a smaller time interval. So when yes, the position difference has not moved as far, but also the time that's elapsed has not moved as far. So you get an average velocity only over these 2 points. What we want to do is figure out the instantaneous velocity at this point exactly. So we keep bringing this point closer and closer and closer and closer, making it infinitely small. And that's what we're basically going to do. So we say closer in time. These are closer in time. Now, what happens if we get even closer in time? Something like this happens, right? So this is x, and this is y. And hopefully I don't mess this up because it's hard to draw when I'm down low like this, but you can see the thing is going to move something like this. And I'm going to have, this is called P1, and so I brought them closer together. Let's bring them maybe even a little bit closer together like here. We'll call this P sub 2. Same sort of thing. P2 is going to have a position vector, tip of an arrow. P1 is going to have a position vector, tip of an arrow. When you take that R2 vector minus that R1 vector, the resultant that you get is going to be a vector that goes from start to finish, which is a very small little arrow right here. And then the average velocity between these 2 points is going to be delta R, which is what this arrow is, divided by delta t. Now, the r vector is smaller, of course, because it hasn't gone as far, but the time is smaller too. So you can still calculate the average velocity between these 2 points there, right? Now you continue this process, and this is what really calculus is about when you get into calculus down the road. You make the position P2 closer and closer and closer to P1 to the point where they're just fractions of a nanosecond up. It's like bammo, then the ball has not moved any distance at all. And you get closer and closer and closer to defining what we call the instantaneous velocity at point P there, right? At point P there. So what we're going to do I want to do it on this page? I think I do, actually. So what I will do is draw our final one right here. So this is going to be our last one. This is x, this is y. And the path is the same exact path. Of course, I can't draw them perfect. You can see, you can already tell that one's not quite as good. But you get the idea. So P point and P2 get closer and closer and closer until finally there really aren't any there's no 2 points separated at all. It's like the 2 points are on top of each other. And I basically just call that point P, or I'll just put a little dot there to say the instantaneous velocity at this point in time, right here, is given by the following. Given by an arrow that goes off in this direction. And we don't call that the average velocity anymore. We just call it the velocity. Because this is an average between 2 points. This is an average velocity between these 2 points separated in time. This is an average velocity when the points are a little closer together. This is an average velocity when the points get very close together. But if I make the points incredibly close together so that they're essentially on top of each other, then I've defined what I call the instantaneous velocity, and I don't call it average anymore. I just say that it's v like this. And I can think of this, unfortunately I've got my arrows, I've got this v in a place that's not going to be great. Let me rewrite this in a second. I can think of this as the instantaneous velocity, and I can think of that instantaneous velocity as having a horizontal and a vertical component to it, like this. So what I can say is that this is the instantaneous velocity at this point down here, and I can also think of the vertical component of this arrow here, I can think of it as v sub y, the y component of the instantaneous velocity, and v sub x, the instantaneous velocity in the x direction. All right? Now, the punchline. Let me get rid of this right here. The punchline is that this instantaneous velocity is going to be equal to the limit as delta t approaches 0 of delta r as a vector over delta t. And I'm going to kind of circle this because it's so important. So, but we basically said is in one dimension, hey, we can define an average velocity between 2 points. We'll just subtract to get the distance the thing moves and divide it by the time it takes. That's an average between 2 points. If we make these 2 points closer and closer and closer together so the time interval is very small, we still measure the very small distance the thing traveled divided by the very small time, and we say that that's the instantaneous velocity in one direction, the x direction, at that point, right? Instantaneous, that's what instantaneous velocity means. It means we've shrunk it down so far that there's still 2 little points there, but they're on top of each other because we allowed delta t to go to 0, the time interval to go very close to 0, never getting to 0, but getting close to 0, and define the instantaneous velocity at that point. All right? And we did exactly the same thing here. The points are separated in time, here's the average velocity. Points are closer in time, here's the average velocity. Points are even closer in time, and here's the average velocity. The points are so close in time that effectively it becomes instantaneous velocity. You still have a velocity arrow vector, but then we say, okay, this instantaneous velocity can have an x component and a y component. That's how things work in the real world. When a baseball goes through the air, at every moment in time, we think of it having a velocity vector arrow pointing in the direction of travel if there were no other forces acting on it. In this case, the thing is turning constantly. There must be some force pushing it. But if there were no forces, that instantaneous velocity arrow would be the direction that it would travel on and on and on forever and ever. And that velocity can be thought of as having an x component and also a y component of the instantaneous velocity. All right? Now, let me write on the other board a couple of things and draw some conclusions. So we just said that the instantaneous velocity is equal to the limit as delta t goes to 0 of delta r divided by delta t. Now, this is not a calculus class, but for those of you who are taking calculus or who are interested in calculus, this basically becomes what we call the derivative in calculus. The velocity is equal to what we call dr dt. These two things are the same thing. When you see dr dt in calculus, what it means is you take the limit as delta t approaches 0 of the change in r divided by the change in time. So it's the same exact thing as this. We just don't call, if you're not taking a calculus-based physics class, we don't talk about derivatives, but this is what it's becoming. This is what the instantaneous velocity is. It's the rate of change of position divided by how long it takes. Meters per second, right? Distance divided by time. Rate of change position with respect to time. Rate of change of position with respect to time. But then as you let the time interval shrink down, then we call it the velocity at an instantaneous point. And every velocity that you see, if you could see all the arrows, you could think of them as having a horizontal component and a vertical component. Every vector you can think of that way. And that is how we're going to treat our motion down the line. If I tell you I have a velocity of 55 meters per second at an angle of 20 degrees, the first thing I'm going to do is break it into horizontal and vertical components of the velocity and work on the different directions separately. All right, it's time to begin our summary. And so I have to write down some important notes. Believe me, I wouldn't include these if they weren't incredibly important. So what I want to do in order to motivate the notes is I want to draw one more time this path that I'm sure you're very tired of, but let's go ahead and just do it anyway. Like this. All right? So we now said that we can have multiple points. We can have point P sub 1. We can have later in time, point P sub 2. We can have much, much later in time, point P sub 3. And if we do this process of taking the average velocity between these points and shrinking it down, we can get the instantaneous velocity at P sub 1. And the instantaneous velocity is going to look something like this. It's always going to be tangent to the path. Tangent means that it just barely touches the path in one point. right? So you can call this the velocity, the instantaneous velocity vector at this point. Now at this point, it also has its own velocity, but it's pointed in a different direction, like this. It has a length and it has a direction. Notice the direction of this velocity is different than this one because the path is changing. But again, this velocity is tangent or just touching this point at the curve at one spot, right? And here you can see that it also has its own velocity, which is, kind of drew that one not so great. Sorry about that. It's going to be more like this, something like this. And it's got its own velocity like this. So at every point, it has an instantaneous velocity, and the point I'm trying to impress upon you is that the instantaneous velocity is always tangent to whatever the path is at that point. So I guess let me write a few more things down, and then we'll talk about it here. So at this point, and at this point, and at this point, the velocity is tangent to the path. And when I say tangent, I'm not talking about trigonometry tangent. I'm not talking about sine over cosine. I'm not talking about the trigonometry. I'm not talking about that tangent at all. I'm talking about tangent is a word in math. That means when two things are tangent, they only touch at one point. So if you have, some curve like this, then there's only one little point on that will be tangent to this side of it. It's going to go something like this. It's going to touch only at one little point. That's called tangent. This part of the curve has one line tangent. This down here has one line tangent. This part over here has one little point tangent to it. Tangent means that it only touches at one spot. And so at this point, the velocity, which is the rate of change of the position with respect to time, it's always tangent to the path, tangent to the path, tangent to the path. Why is it tangent to the path? You can see that when you start the calculation for the average velocity, it's not tangent to the path. It's not even tracing over the path. It goes under the path. But as you bring them closer together, it gets closer and closer until it's exactly only touching the path in one spot. And that's because of this process that's happening as we essentially it's calculus, but as we bring them together and indicate the instantaneous velocity, it becomes exactly tangent to the path. All right, we can also talk about, I mentioned it down here verbally, but we can talk about instantaneous velocity in components. So this equation right here, let's see here. The instantaneous velocity is the limit delta r over delta t. This is the vector equation, but we don't have to write it in vector terms. We can think of it in terms of components. We can say that the x component of the velocity, of the instantaneous velocity, delta t, goes to 0, delta x, delta t. All we do is we see how far did it go in the x direction, divided by the time, and we let that shrink down and we get the instantaneous velocity in the x direction. All right, and Vy, we could do the same thing. We could say the limit as delta t approaches 0, delta y, delta t. How far did it go in the up and down direction divided by how long it took and shrink that guy down as well. So this is the instantaneous velocity in the x direction and the instantaneous value in the y direction. And I think what I'm going to do is leave you with one last picture to understand this. I'm going to draw this one more time. Sometimes drawing things over and over again, it helps me and it also helps you because you see it a bunch of times. So what we're going to do is I'm going to draw the same kind of deal, a nice curved path like this. I'm going to pick one point right here, like this. And this is point P, right? And what is its velocity? Well, it's got to be tangent to the path here, so it's got to come out something like this. And then what we can do is we could say, all right, this is the velocity, like this, and we already said that it can be broken down into x and y components. So this is v sub x, and this is v sub y. So all I'm saying here is that when we figure out the instantaneous velocity in 2 dimensions, it's really going off in this direction like this, but you can think of it as a horizontal velocity and a vertical velocity, which add to give you this guy here. And the horizontal velocity is just delta x over delta t, and you let it shrink down and get the instantaneous horizontal velocity. And you do the same thing vertically. How far is the thing going up compared to how many seconds it takes? And you let that thing shrink down, delta t over 0, and do it in the vertical direction, and you get the vertical component. Notice that the horizontal component plus the vertical component, because these are both have direction as well right here. And when you add them up, what do you get? You get the slanted instantaneous velocity vector v right here, right? And then you can say that the magnitude, which is the length of v, the speed, which is what we call the speed. Remember, speed is just how fast something is going. Velocity is how fast and in what direction it is going. So the magnitude of the vector, which we call the speed, is just the length of this vector. And from Pythagorean theorem, you can see that it's going to be the square root of vx squared plus vy squared, right? And then we can say that the angle of the velocity vector, that the angle is equal to the inverse tangent of what? Just from trigonometry, the y component divided by the x component. So vy, vx. A lot of times, a problem will say, here's what's going on, and what is the angle of the baseball? What they want you to tell them is, figure out the velocity vector, which and how is it slanted, and tell me what the angle is. And so you can see that there's an angle right here. I'll draw it right here. Call it angle theta, and this angle is going to be the inverse tangent of the y part of this triangle divided by the x part of this triangle. And from trigonometry, you know the inverse tangent is going to give you that angle here. So the direction of travel, and as time changes, as this ball flies up like this, then of course the x and y components of the instantaneous velocity are going to change. As time goes on, you know, over here it has a very high vertical velocity and a very small horizontal velocity. So Vx is small and Vy is big. And as it gets over here, Vy becomes small and Vx gets big. So as the ball travels, these little components are shrinking and growing. The sum of those components give you the velocity vector V, which is always tangent to the path, right? Now, if this were, you know, on some kind of string or something like that, and I cut the string, then this thing would fly out. You can think of almost like the sun being down here and gravity is like causing it to curve. So that's why it's on a curved path. This velocity vector is the direction it would travel if everything was, if you cut all ties, no forces, nothing, it would just continue going in a straight line. We're going to talk a lot about Newton's laws of motion very, very soon. So I'm kind of getting ahead of myself. But basically the only way this thing can continue on a curved path is if something is pulling it and making it curve, like the force of gravity causes a ball to be thrown to be pulled and curved. If there's no gravity, like in space, the ball just goes on forever. So if there's no gravity causing this thing to turn, then the ball just continues to go in this direction. So all of these tangential velocities, these instantaneous velocities, this is the direction the ball would go. If you immediately cut off gravity or whatever other force is pulling it, they would just fly off in a straight line direction like this. Now, we're done, essentially, but I'm going to draw one last thing with you, and I want to give you a little motivation and talk about what happens in 3D space. Right? We're not going to do any problems in three-dimensional space, but I think it's important for you to know what's going on here. So in three-dimensional space, you have a little more of a complicated situation like this. And this is the x direction, and this is the y direction, and up here, this is the z direction, right? So you can think of this plane down here being the xy plane. This is the same plane that we're drawing on the board, but we lay it flat. We call it the xy plane, and then up from that comes the z. So now every point in space has an x component or an x coordinate, a y coordinate, and a z coordinate. So the vectors you draw for the position have x, y, and z component, coordinates there. So again, we're not going to do any problems with this, but it's pretty easy to visualize. Let's say that we have point, we'll call it P sub 1 right here. And this is a point in three-dimensional space. So how do we draw that? Well, we have to have a position vector that goes from the origin straight up right here. We call it R sub 1. It's exactly the same thing we did before, but the only real difference is that because this is 3 dimensions, I'm going to draw something to kind of help us visualize what's going on here. So this is like, you can see this point is not in a plane. It's kind of coming out towards us here. This point is like raised off the board, like out here, but this straight line distance from the origin is still what we call vector R1. And then over here, I can call this guy over here, I can call it, let me switch colors back. I can call it point number 2. Guess I really didn't switch much colors there. But you get the idea. And I can keep track of its position with a position vector also, and this position vector I can call R sub 2, right? And just to keep track of it, to make it a little clearer, I can say, all right, I can drop this guy down here, something like this, all the way over like this, all the way over like this. You get the idea. These points, P1 and P2, they're not in the plane of the board. They're lifted out of the plane of the board. But still, the straight line distance from the origin to here is a position vector. Straight line distance here is a position vector. And you can say that the vectors R1 and R2 have an X component and a Y component and a Z component because we have three numbers in our coordinate system now. And then you can say that the velocity, as the particle goes from P1 to P2, the average velocity, or the instantaneous velocity, you could say, would look something like the limit as delta t approaches 0 of delta r over delta t, right? What would that path look like? I don't know, I could draw something. Maybe the path starts out over here and it goes down, something like this. So the particle is now a ball which flows through three-dimensional space, goes through this point, comes out and hits through this point, but you see the math is the same. That's all I'm really trying to get at you. You might think 3 dimensions is going to have totally new equations, but actually this is the exact same equation that we actually talked about earlier. If I can find it. Yeah, it's the same exact equation. It's really no different. The only difference is the position vectors that are the tip of the arrow to each point in space, they now have X, Y, and Z coordinate values. And later on, when you get to like relativity theory, we have time as its own independent coordinate also, and things get totally different, okay? So now what I'd like to do, we've gotten through it, but sometimes we all benefit, including me, of going back through the whole thing. Now, again, I could have just started from the beginning. I could have just said, hey, here's some equations, use them. And what I would have done is I would have said, okay, in one dimension, the velocity is the distance divided by the time. We call it delta x divided by delta t. The instantaneous, when you shrink everything down, is delta x divided by delta t. You take that limit as the points get closer together, we call it instantaneous. And then what I could have done is I said, okay, here's the average velocity. Notice it's just delta r over delta t. And then you would have said, okay, well, that just looks like the other equation. And you would have been, okay, on your happy, merry little way. You wouldn't have known the kind of the grander, the grandness of any of this stuff. You wouldn't have known how any of it worked. If I just basically put this there to you and said, this is the position, this is the time, there it is in two-dimensional space, then you would have been, okay, great. But you wouldn't have gotten any of this here. And so I'm hopeful that this is kind of like broadening everybody's horizons here, okay? So what we want to do, or what we did, is we said, we want to figure out what the average velocity is as the point moves between point 1 and point 2. So we say, we now have to keep track of its position with an arrow called a position vector. The position vector is r with a little vector symbol on top. The tip of the arrow represents the point P. As the point P moves through space, as it goes from P1 to P2, the arrow, we changed it to denote a new final position, but it gets longer and it also changes angle. So the unique tip of the arrow, the position vector, denotes where the particle is. Now, how do we define the average velocity? We say, well, its final position minus its initial position must tell us how much it moved, and then we divide by the time. And then we say, okay, final position minus initial position, but now they're vectors, divided by the time, which is delta r over delta t. That's what we have to calculate. We also said that for every position vector, it forms a triangle, and so the length of this arrow is the distance from the origin, and that's just from the Pythagorean theorem, x squared plus y squared, and we take the square root. So this average velocity equation looks very, very close to what we did in one dimension here. The only real difference is we have vectors on the top, denoting the final position and the initial position. So what we did is we said, okay, the final position was this, we already had that drawn, but to subtract the initial position, we flip it around so the arrow points down, and that makes it negative r. So now we add these vectors, which becomes then r2 minus r1, and that is a vector that goes from the starting point to the ending point. So when you subtract two position vectors, you get a new vector which points from start, P1, to finish, P2. That indicates the path, basically, over which the thing moved from start to finish. It indicates the displacement vector from start to finish. And that's what this purple vector is right here. So now we erase all the scaffolding and we just say from point P1 to P2, the position or the displacement vector difference, R2 minus R1, just starts here and it ends up here. We take that vector, we divide by delta t, the time elapsed, we get a new vector called the average velocity. It's in the same direction, but it's going to be a different length because we're dividing by time. We're just scaling it, making it either bigger or smaller. So there's the velocity. So the average velocity goes in the same direction, pointed from P1 to P2. That's what I want you to know there. And then we start talking about components. We say that's the vector velocity, but we can think of it in terms of an x component of average velocity and a y component of average velocity, where the x component of average velocity is just how far it moved in x over the time interval, and the y component of average velocity is how far it moved in y. So from here to here, it moved this far in x, that's delta x, and then we divide by time. And then it moved this far, that's delta y, divided by time. So we can calculate the x and y components of average velocity by looking at how far it moved horizontally and vertically there as well. And these two average velocities will kind of combine to give us the velocity between this point here. So now we want to go towards the idea of an instantaneous velocity. We start with our normal P1 and P2, and we get that the average velocity is the delta r divided by delta t, and this is representing the velocity between these 2 points. As we bring P2 closer, we're using the same equation. The displacement gets smaller, but the time is getting smaller as well. So when we do that division, we're getting a new average velocity, which is more accurate the closer and closer and closer we get to where we're trying to go down here. Now we make them very, very close. Again, the displacement is smaller, but the time is even smaller. We're getting more and more accurate as to the instantaneous velocity down here right on top of P1, until finally, with the magic of calculus, if we let the time interval approach 0, then the displacement is infinitesimally small, but the time is also infinitesimally small, and we end up with something we call the instantaneous velocity at this point. And we can also think of this instantaneous velocity being the red arrow, which can have components in the x direction, which would be pointed this way, and the component in the y direction, which would point that way. And they combine to give you the instantaneous velocity there. And then we say, all right, so here, as we just rewrote the same thing again, the instantaneous velocity is equal to this. And we say in the terms of calculus, you might think this is starting to look a lot like calculus, and it is. When you take the limit of a quotient like this, it's the same as what we call the derivative of the position with respect to time. How much does the position change with respect to time? Rate of change of position with respect to time. That's what a derivative is. This is not a calculus-based lesson right now, but does have strong tie into calculus, so I wanted to mention it to you. And then we say, as the ball flies along at different points in time, P1, P2, and P3, it has different velocities, which are all oriented tangent to the surface. And the reason why the velocity vector is always tangent to the actual path of the surface is you can kind of see that here it undercuts the path, and then it starts to agree more and more and more with the path until finally it just barely touches the path. That's called tangent to the path, whenever it barely touches in one little spot. But then this instantaneous velocity can have x components and y components as well. The x, delta x divided by delta t, and delta y divided by delta t, as the time approaches 0, gives you the verticalness of the instantaneous velocity and the horizontalness of the instantaneous velocity. You can see it better here. If this is the velocity, the instantaneous velocity in the x direction is this direction, and the vertical velocity is this direction. And when you add them together, you can see that you're going to get the same total velocity in this direction here. Now, what we call the speed of an object is just how fast it's moving, irrespective of its direction. And so that's the length of this arrow. So when you want to know the magnitude or the strength or the magnitude is the best word to use for a velocity vector or any vector, you want to find the length of the arrow. From the Pythagorean theorem, we can find it easily by taking the square root vx squared plus vy squared. And the angle of this thing compared to the horizontal is the inverse tangent of this component divided by this component. And then we said that you can extend this thing to even more dimensions. 3D space, you're still going to have point number 1 and point number 2. This vector will have x, y, and z components. This vector will have x, y, and z components, but to find the velocity, you're doing the same thing. You're subtracting them, you're dividing by the time, and then you're taking the limit as delta t goes to 0. So this equation is exactly the same in 3-dimensional space as it is in 2-dimensional space. The only difference is in 3D, your position vectors will have x, y, and z components. And so it makes it more complex. And if you think of components x, y, and z adding up to the total motion that you have, then you can see how the components add together. This was a long lesson, and believe me, I struggled with how much of it to give you, because I could do it the way I learned it, and I could have just said, hey, yeah, the velocity is equal to this. Oh, this limit, don't worry about it. It's really just the distance divided by the time. And you would have probably got enough of it to do a few problems. But then when we get a little farther down the road, especially with angular momentum and other things we're going to cover later, if you don't really know how the vectors add up, then you don't really know what you're doing. I mean, you're faking it, essentially, is what you're doing. And the key thing that I really wanted to get across in this lesson, the key thing is how do you start in position number 1 right here, and then end up sometime later in position number 2 with these two different displacement vector position vectors? And how do you calculate this in such a way that makes sense? Why does the resultant vector start here and end here as we showed it here? Why does it do that? Because I can draw that for you in a book. Most books just show you that it happens, but you don't know why it happens. And now you know that you're doing the same thing you're doing in one dimension. Final position minus initial position. Final position minus initial position. It's just that in order to do the minusing, you have to flip the direction of this vector and then connect it. And so then the arrow goes from initial to final state. I could go on and on through this again and again and again. Eventually, I just get to repeating myself. So what I would like you to do is please watch it at least twice. And I do mean that. Because, if you gloss over things or say, well, I don't care about that, I'll just use the equation, just solve the problems. I mean, that's fine. It'll get you a little ways. But eventually, you'll be like, why does this happen this way? And it'll be because you don't really know how vectors work. How graphically, when you subtract two vectors, you flip it around, and then it has to go from start to finish because that's the way it works. You'll just kind of like assume that it works, but we won't know why it works. That's why I went through all this trouble. So please, watch it 2 or 3 times. I did not learn this stuff until a little bit later, certainly to this level of detail. But once you have this, once you understand what's going on and that the components, the X and Y components, we treat everything separately in terms of components in physics. That idea is going to be critical. We're going to do that a lot with problems. So I'd like you to watch this and then watch it again, and then maybe even watch it again. And then follow me on to the next lesson where we're going to not talk about position and velocity, but in the next lesson, we're going to talk about acceleration in 2 dimensions.